should be able to come away from this video lecture being able to define the oxidation reduction reactions, okay, and to differentiate between oxidation and reduction processes. So we're going to be looking at oxidation reduction reactions, otherwise known as redox reactions. Basically, an oxidation reduction reaction is one in which electrons are transferred from one reactant to another. And basically what ends up happening is you undergo two processes. You have an oxidation process and a reduction process. The oxidation process is the loss of an electron by a substance, while the reduction is the gain of an electron by a substance. So oxidation, or that process of those losing electrons, has been something that has been viewed from the perspective of oxygen being the substance that reacts with a metal in order to produce oxidation. However, what needs to be understood is that that does not only occur between metals and oxygen. There's other oxidation reduction processes, but basically this nomenclature, this oxidation nomenclature, comes from reactions in which oxygen react with a specific metal. Now you guys have seen these in textbooks and everything else, but the fact that the copper is this nice green color on the Statue of Liberty, or rusting of your bike and tarnishing, things of that sort. Those are all examples of oxidation processes that occur when specific substances, specifically metals, are in the presence of oxygen. So oxidation reduction processes are things that we see regularly, we inherently understand in terms of a visual cue that something has changed. We have chemical changes. However, understanding what's physically happening between our reactants is what we need to glean from this lesson. So if we think about this from the perspective of reactivity, we want to think about the valence electrons that are being used in these processes. So we know that calcium has 2 valence electrons, while oxygen has 6 valence electrons. So in order for either of these elements to be able to form their octet or to be in their most stable states, they're either going to be losing or gaining electrons. And you know, they can do this by sharing, they can do this by electron transfer. In this situation, because we're dealing with metals and nonmetals coming together, it's typically going to be that electron transfer process. So calcium, we know, is one of the metals. Metals like to give up their electrons. In this case, we have 2 extra. So if we lose 2 electrons, we end up with the calcium 2+ ion. Same thing here, same concept. If we gain these 2 electrons from that calcium, our oxygen is now going to have its octet and be a 2- ion. These two come together and give you your calcium oxide product. So what you guys have to understand is that the transfer of electrons is not electrons coming from, you know, outer space or the middle of nowhere. The reality of it is that the electrons are coming from each of the reactants and being accepted by the reactants that are present in that specific reaction. So electrons are not coming from nowhere. They're basically being exchanged between your reactants that are involved. Now, please remember that oxidation reduction reactions can occur in different scenarios and different situations. It doesn't just have to be this metal-oxygen construct that we have here. However, it allows us to very easily see how this process actually works. The following lecture will allow you to identify oxidation numbers, okay, based on the provided protocol that follows, and you will be able to identify redox reactions by oxidation number changes. Okay, so let's go ahead and let's look at this example right here. Na2O, so sodium oxide. Okay, sodium oxide is an ionic compound. I know in this situation that I have sodium. Okay, and sodium has a +1 charge. Oxygen, this is not the peroxide situation, so O2- is what I have there. Okay, please notice though that I have 2 sodiums. Okay, so I have 2 +1 oxidation numbers, yes, okay, plus the 2- oxidation number here, so that gives me an overall oxidation number of 0 in terms of their sum. So how would I label this? I would label this as +1 I would label this as -2 in terms of oxidation numbers. Okay, and basically this is how I would do my labeling. Same thing here. Okay, hydrogen, remember we said it's +1 unless it's attached to metals. Sulfur is not a metal, so sulfur is not going to be changing the oxidation number setup for hydrogen. Sulfur in this case is a -2 in terms of oxidation number. I know this because I have two positively 1 charged hydrogens. If I sum the two together, I have 2 + 1 oxidation numbers plus a -2. That gives me an overall 0. So the next example is a little bit more complicated. Potassium in this case, we do know that it's +1 because potassium ions form +1 charge. Okay. In this situation, though, we have a polyatomic ion. Now, the charge on this polyatomic ion is 2-. The reason why I know that is 1, because I've memorized it off my list, and also because I have 2 +1 charged potassium ions present. So in order to figure out the oxidation numbers associated with the sulfur and the oxygen, I must basically break that off as its individual pieces and then subsequently assign to each individual atom. So the way I would approach this is basically first look at the one that I know. So oxygen in this case, this is not peroxide, right? This is just oxygen atoms in a molecule. So oxygen typically has a -2 charge, right? So I have a -2 charge coming from each of the oxygens present. Each oxygen present is going to contribute to the overall charge of the molecule, right? So -2 times 3 is going to give me -6 coming from the oxygens. Now, -6 is what's coming from the oxygens, and this sulfur subsequently has to have a charge that's going to balance the -6 coming from the oxygens and still maintain a -2 charge coming from the overall molecule. So what am I going to do? I'm just going to do a little bookkeeping down here for my own personal bookkeeping system. Okay, so oxygen is contributing -6. Okay, I need a -2 charge, so I'm going to need a +4 here on the sulfur. Okay, 4 minus 6, right, is going to give me overall -2, so that makes sense. So my sulfur is going to have a +4 charge, and each individual oxygen is going to have a -2. So if I bring this back to the original molecule, okay, I have a +1, I have a +4, okay, and I have a -2. And if I look at this with respect to the overall charge, if I look at the K2SO3 molecule, I notice that there's no charge there. And if I look here and I count up all my pieces, I have 2 potassiums with a +1 oxidation number, plus 1 sulfur with a +4 oxidation number. That gives me a total of +6. Oxygen here, there's 3 of them. Each one has a -2. So 3 times -2 gives me -6. +6 plus -6 is going to give me an overall oxidation value of 0, which matches what I see here. So basically there's some bookkeeping involved here. What I want you guys to make sure that you're paying attention to is that you are not putting the total contribution from all 3 of the oxygens up here. Okay, so each one of these oxygens is a -2 in terms of oxidation number. So you're not putting the -6 up here, you're putting -2. Same thing here for potassium. I have 2 potassiums. Each one of them is a +1 charge. It's not +2 as in the total charge coming from both K2 or potassium atoms. Okay, so paying attention to that detail will help alleviate some of the problems some of you might run into. Okay, so we can do the same example down here with a sulfate ion. Okay, same thought process what we saw up above. In this case, though, we don't have to worry about the potassium situation. Okay, so we're going to look at oxygen, right? Oxygen normally has a -2 charge, right? This is not an example of a peroxide. So what we're going to do is oxygen has a -2. 2 times 4 is -8, right? Okay, the overall charge of this ion is -2. So I have to have a charge on my sulfur that balances the -8 that's coming from the oxygen, but continues to keep the overall charge of the molecule. So 2- is what I need. So +6 is what we're going to have here as our oxidation number, because Positive 6 minus 8 is going to give me minus 2. So in terms of assigning oxidation numbers, we're going to have plus 6 for our sulfur and minus 2 for our oxygen, and the sum of those with respect to the individual atoms present gives you an overall oxidation number that is a minus 2. Okay, so guys, this is the basic approach to assigning oxidation numbers. Being able to assign these numbers is something you want to practice, you want to get involved in, because it's necessary for you to be able to do the next step.
Before we get started with oxidation numbers, I want to make sure that everybody understands that oxidation numbers, except for in a few specific situations, is honestly just a series of imaginary numeric values that we assign to specific atoms and compounds. And these numbers are basically a simple bookkeeping system that allows us to identify the most likely oxidation state or the most likely oxidation characteristics of specific atoms in compounds. Okay, so remember, this is an imaginary system, but it works very well for the identification of the items being oxidized and reduced in chemical processes. So now that we understand that, let's go ahead and let's look at oxidation numbers and how we're going to identify them. So the first thing is that, guys, anytime we're dealing with monoatomic ions, so basically an element that is in its ionic state, so either it's a lost or gained electrons, in those situations, those ions are always going to have oxidation numbers that are the same or equal to the charge on the ion. So the examples that we have here, the sodium, sulfur, and oxygen ions, they each have a specific charge. That specific charge corresponds to their oxidation numbers. Now, for any atom that's in its elemental form, the oxidation number for that specific element is always going to be 0. Okay, so if I just had potassium by itself, okay, or if I had sodium by itself, right, each one of these are in their natural elemental state, so their oxidation numbers would be 0. Now, elements that occur in, let's say, a diatomic form, such as H2 or N2, they are also still in their elemental form, so their oxidation numbers will still be 0. Okay, so please make sure that you remember those diatomics that you're supposed to be familiar with. Okay, now for our third rule here, in the case of compounds, nonmetals are usually going to have negative oxidation numbers. And we know that this is the case in many examples, but in the case of, say, ionic compounds, we know that typically the metal is going to have a positive charge, and the nonmetal is going to have a negative charge, right? So in this case, oxidation numbers of +1 and -1 will occur respectively. Okay, so typically the nonmetals pick up those electrons because they want to be like their nearest noble gas, which usually requires the acceptance of electrons. And so remember that the oxidation numbers are a model of what actually happens. It's imaginary, but in our understanding of chemistry, typically the nonmetals want to take electrons to be like those noble gases. Okay, now let's go ahead and move on to oxygen. Okay, oxygen usually, okay, now notice I'm underlining the word usually, has a charge of, or an oxidation number of -2. Okay, this is true for most situations, except for a few examples. A specific example that will come up are substances known as peroxides. When you see a peroxide present, you know that that charge on that oxygen is going to be -1. Why? Because there are 2 oxygens. This ion overall has a 2- charge, so each one of those oxygen atoms has a -1 oxidation number. Okay, and peroxides will usually show up like this. Okay, N2O2, H2O2. Okay, there are other examples. The way that I always approach these problems is that I always look at what I have over here. So notice that the sodiums here and the hydrogens here, each one of those will have a +1 oxidation number, okay, or +1 charge. And with that being the case, that means that since there are 2 sodiums over here, that this right here has to be a peroxide ion. Same thing is true here. Okay, and if it's a peroxide ion, that oxidation number will be -1 and -1 respectively. So make sure you keep an eye on it. Sometimes these can get you caught up a little. So hydrogen usually has an oxidation number of +1 when it is bonded to nonmetals. So examples such as HCl. Okay, very simply, we know the chlorine is going to have a -1 charge. Okay, so hydrogen therefore is going to have a +1 charge. This is the typical situation. Another option, H2O. Okay, we know that oxygen is -2 except for those the example we talked about before. And hydrogen therefore will be +1. Now this is true when you have hydrogen attached to non-metals. Okay, but when you change that up and you attach hydrogen to metals, you get what's known as a hydride. Okay, so something like NaH. Okay, notice that hydrogen is now attached to sodium. We know that sodium is going to have that +1 charge, or that +1 oxidation number. Okay, so if it has a +1 oxidation number, the hydrogen by default has to be a -1. Okay, so hydrides show up when hydrogen is bonded to a metal. Okay, and this has to do with how the hydrogen itself is behaving. So in the case of a hydride, okay, hydrides are hydrogen atoms, okay, or rather hydrogen ions, I apologize, that have 2 lone pairs of electrons. Okay, if we look at the examples over here, okay, these are known as protons, which you guys have discussed in acid-base chemistry, and in this case, hydrogen has no electrons. Okay, so in this context, the hydrogen has electrons. In this case, the hydrogen doesn't have electrons, and the behaviors are very different. So in this case, we know that the H plus, or the proton, is going to behave as an acid in solution, and so in this context, the hydride is going to behave as a base. Okay, and this will come up later on when we talk more about acids and bases, but just so you're getting the difference between the H plus, or the +1 ion oxidation number that we have here versus over here, that hopefully will help you out a little. Okay, so let's go ahead and let's go with fluorine. Fluorine always has an oxidation of -1. It's the most electronegative element, so it's the one on the table that's most desiring to have that set of electrons, or that negative charge. Okay, now other halogens can also have a -1 oxidation number. However, they can also have positive oxidation states, and this usually happens when they are bound to oxygen. Okay, so let's go ahead and let's look at an example like something like this. Okay, all right, we have this ion. We know that our oxidation number on our oxygen is going to be -2, right? So in order for the overall charge of the ions to balance, I'm going to have a +1 oxidation number on my chlorine. Okay, because -2 + 1 gives me -1 overall, which matches with the overall charge of the ion. So the final consideration is that the sum of all the oxidation numbers in a molecule must equal the overall charge of that specific molecule. Okay, and we just saw that in the example above. Okay, each of the oxidation numbers here have to add up to what the overall charge of the molecule is. So if we look at our charge of this molecule here, -1 is that charge. Okay, and each atom here has an oxidation number. So the oxygen has a -2, the chlorine has a +1. So -2 + 1 equals -1, which matches our overall oxidation number. If we go ahead and look at another example, let's say CO3 2-, okay, the overall charge here is 2-. Okay, so if we go ahead and assign our oxidation numbers, oxygen is going to be -2. Okay, and there's 3 of those, so 3 times 2 is -6. Okay, so that's -6. Right, so in order to get an overall -2 charge, okay, carbon is going to be +4. Okay, so +4 - 6 equals -2, which matches with the overall charge of the molecule. Now, if there is no charge to the molecule, if it's neutral, okay, so let's look at like H2O, that's a neutral molecule. Okay, oxidation number here is -2. Each one of these hydrogens have a +1 oxidation number. Okay, so -2 + 2. Why? Because there's 2 hydrogens, each with a +1 oxidation number, and that will give us an overall charge of 0, which matches with the overall the overall charge of the molecule of water. So the identification of redox reactions involves a 2-step process. The first step is to assign oxidation numbers for all of the elements on both the left and right-hand sides of the arrows. And the second step requires you to check for any changes in specific species on the left and right hand sides. So what is meant by that is once we identify the oxidation numbers on this sodium on this left hand side of this arrow, we would compare it to the oxidation number of the sodium on the right hand side. And if there is a change in the oxidation numbers from the one on the left versus the one on the right, that would indicate that a redox process has occurred. Okay, so let's go ahead and let's follow through with this procedure. Okay, so the first thing we're going to do is identify our oxidation numbers of all of our reactants and our products. Okay, so sodium is a lone element all by itself, so its oxidation number is 0. Chlorine as well is a lone element. So it will also have an oxidation number of 0. Sodium chloride is a compound. It's an ionic compound, so the components that exist in the compound are ions. With that being said, we know that sodium is going to be a +1 ion and chlorine is going to be a -1 ion. Okay, so once we've identified the oxidation numbers on both the left and right hand sides of the arrow, we're then going to compare those values. So if we look at our sodium here and we compare it to the sodium on the right hand side, we notice that we go from an oxidation number of 0 to an oxidation number of +1. Okay, so that is indicative of a change in oxidation state. Okay, and when we look at the chlorine oxidation number, which is 0 here, and the chlorine on the right hand side of the arrow, its oxidation is -1, so we also see a oxidation number change in this situation. So a redox process, okay, has occurred in this reaction, and we subsequently see that we have lost and gained electrons. In the context of sodium going from an oxidation number of 0 to +1, okay, we know that we have lost 1 electron for every sodium atom. And we know in the context of chlorine, we know that each of the chlorine atoms has picked up 1 electrons. Okay, so we have found our oxidation process, and we have found the substance that has been reduced. So we're going to go ahead and assign our redox numbers for this reaction here. So potassium iodide is an ionic compound. Potassium is going to have a +1 oxidation number. Iodide is going to have a -1. The lead that you see here is going to be in the +2 state because we have 2 nitrates that are attached, and each nitrate has a -1 charge, so that +2 ion is going to have a +2 oxidation number. We can go ahead and figure out that each of our oxygens are going to have a -2 oxidation number as usual. Okay, so -2 times 3 gives us -6. So +5 is nitrogen's oxidation number to give us a -1 overall for each nitrate. Okay, if we come over here to our right-hand side of the arrow, the lead ion is going to be +2 oxidation number because there's 2 iodides with a -1 oxidation number each. Okay, and with potassium, once again, +1, and the same oxidation numbers for the nitrate ion here on the right-hand side. Okay, so once again, we're going to look at these and see if there's any changes. Okay, so if we go ahead and take a gander at potassium, potassium is +1 on the left, +1 on the right. Iodine is -1 on the left. It's also -1 on the right-hand side of the arrow. Lead is +2, lead is +2. Nitrogen is +5, nitrogen is +5 on the right, oxygen is -2, oxygen is -2. Okay, and what we see here, guys, is that there is no change in the oxidation states for any of the examples that are on the left or right-hand side. Okay, so in this case, we know that this reaction is not redox. Okay, so electron transfer has not occurred in this reaction. Now, this is not to say that this reaction has not occurred. Okay, this is a very simple double replacement or metastasis reaction that you guys have probably seen in previous classes. Okay, so the reality of it is that this reaction, even though it does occur, it does not occur by the transfer of electrons between species. It is not redox. So very simply, in order to identify a process as redox, you're going to assign those oxidation numbers, and then you are going to check for changes on species in the left-hand side versus the right-hand side to identify if redox has actually occurred.